Okay, so in section 5.3, we're going to be looking at our final method for solving linear systems, which is referred to as the elimination method, and you'll see why that is in a second. Your textbook calls this solving by adding, and you'll also see why it's sometimes elimination method is sometimes referred to as solving by adding. But I think it's more commonly referred to as elimination method, and I will be referring to this method as elimination method. Okay, so elimination method is the second algebraic method for solving systems of linear equations, right? The first method we looked at was graphing the linear system and finding the point of intersection. Then in section 5.2, we looked at solving linear systems by substitution, where we solved for one variable and then substituted that quantity into the other equation, and that allowed us to solve the system. So the process of elimination attempts to eliminate a variable by adding the equations together. So sometimes the variable is not easily eliminated, and when that's the case, we have to use the multiplication property of equality to one or both of the equations as a means to line up one of the variables in order for them to eliminate when we add the equations together. So the goal is to arrange the equations such that either the x terms or the y terms are opposites, right? Opposites refers to opposite sign. So that when the equations are added, the terms will eliminate. So for example, we want, like, the opposite of 2 would be -2. 2 plus -2 is 0. Or the opposite of -5 would be +5, because -5 plus 5 would be 0. So we want the coefficients of either the x terms or the y terms to be opposites of each other. And we can make that happen by using the multiplication property of equality when necessary. So let's look at this first equation, this first system of linear equations. I'm going to call this equation 1 and this equation 2. Okay, just to help keep us organized. Notice that our x terms are lined up and our y terms are lined up, which is what we want. And the coefficients of the x terms are both 1. The coefficient of the y term in the first equation is 1, and the coefficient of the y term in the second equation is -1. Well, 1 and -1 are opposites of each other. Therefore, if we add these two equations together and we add straight down, we'll have 2x 1y plus a -1y would be 0y. So the y's end up eliminating. And then 5 plus 1 will be 6. Okay, so notice now we have an equation that has only one variable in it. So we can actually divide by 2, so finish solving this equation in order to get the value for x. So for the solution to this system, the x coordinate is going to be 3. And then just like in substitution method, we can plug x equals to 3 into either of the equations in order to solve for y. So since in the first equation y has a coefficient of 1, I'm going to take the first equation and substitute 3 in for x. Okay, you could use either equation though. And then now if I subtract by 3 on each side, we will get y is equal to 2. And then remember, the nice thing about solving linear systems is that we can check that our solution is correct by substituting our ordered pair into both equations to make sure that it satisfies both equations. So we would have 3 plus 2 equals to 5. We get 5 equals to 5. So the first equation checks. And then we would have 3 minus 2 equals to 1. and 1 equals to 1, so that checks. So the ordered pair 3, 2 satisfies each equation, meaning it's a point that lies on each graph, and therefore must be the point of intersection, which means it's our solution to the system. Okay, so we did not have to use the multiplication property of equality in this example. Sometimes you will, sometimes you won't. All right, so let's look at this next example. Here, we'll use a different color. So I'm going to call this equation 1 and this equation 2. Okay, so our x's are lined up, our y's are lined up, the constants are lined up vertically. However, the coefficients for the x's are not opposites and the coefficients for the y's are not opposites. However, I can multiply the first equation by 2. So on each side of the equation, multiplying by 2. So that gives us 4x plus 2y equals to 14. I don't need to multiply the second equation, okay, by anything. Because notice now the y's have opposite coefficients, okay? So when we add the two equations together, we add straight down, so 4x plus 3x is 7x, and 2y plus negative 2y would be 0y. Okay, 14 plus negative 7 will give us positive 7. And now we can finish solving for x just by dividing by 7 on each side. So we get x is equal to 1. So we know the x coordinate for our solution will be 1. And we can plug 1 into one of the equations. I would substitute x equals to 1 into the first equation. I'm going to come over here. But it doesn't matter which one, so that's going to be 2 plus y equals to 7. Subtracting by 2 on each side of the equation, we'll have y is equal to 5. Okay, and then let's go ahead and check. So checking in the first equation, we get 7 equals to 7. That works. And then let's check in the second equation as well. You need to check in both. The ordered pair could satisfy one equation, but if it doesn't satisfy the other, then something went wrong and there's an error. So it's going to be 3 minus 10 equals negative 7. Negative 7 equals to negative 7. So the left-hand side equals the right-hand side. That means 1, 5 satisfies the second equation in the system as well. So 1, 5 will be the solution to this system. Oops. Okay, looking at this system, I'm going to call this equation 1, equation 2. X's and Y's are lined up and constants are lined up vertically. However, we don't have any opposite coefficients. Now, you can make, it's up to you. We're going to have to use the multiplication property of equality here. And it looks like since all of the coefficients are prime numbers, we're going to have to multiply both equations by a constant, and it doesn't have to be the same constant. But I noticed that the y terms have, in the first equation, the coefficient of the y term is negative, and then in the second equation, the coefficient of the y term is positive. So those are already opposite signs. So the least common multiple of 3 and 2 is 6. So I'm going to choose to multiply the first equation by 2 and the second equation by 3. This is not your only option. You could also multiply, the least common multiple of 5 and 3 would be 15. So you could also multiply the first equation by 3 and like the second equation by -5 to make them opposites of each other. It's up to you. Okay, I just like whenever there's one coefficient that's positive and the other that's negative, then I know I don't need to multiply one of the equations by a negative number. I can just multiply them by positive values. Okay, so then when we do that, I'll have 10x minus 6y equals to -2, and 9x plus 6y equals to 21. Okay. So now the y's have opposite coefficients, so I'm ready to add. I'll get 19x equals to 19. So we can divide by 19 on each side of the equation to get that x is equal to 1. So we know that 1, as long as we haven't done anything wrong, 1 should be the x coordinate to the solution. And it doesn't matter which equation we substitute 1 into to find the y value. I'm going to take equation 2, just since there's all positive coefficients. So 3 times 1 plus 2 times y equals to 7. So that's 3 plus 2y equals 7. 2y equals, subtracting 3 from each side of the equation, we'll get 2y equals to 4. So then when we divide by 2, we get y is equal to 2. And then let's make sure we check. So checking in the first equation, whoops. So it's 5 minus 6 equals to -1. So we get -1 equals to -1. And then checking in the other equation, we get 3 plus 4 equals to 7. 7 equals to 7. So both equations check. 1, 2 is our solution, the ordered pair, 1, 2. Okay. So for this next system, notice that we do not have our x's and y's and constants lined up vertically. So we need to fix that first. So in the second equation, I'm going to subtract 4x from each side to rewrite the system. So the first equation will stay the same. The second equation will be -4x plus 3y equals to 1 once I subtract 4x from each side. Okay, and then neither of the coefficients are opposites of each other, so we're going to need to use the multiplication property of equality. I know that 3 is a factor of 12. So if I multiply the second equation by -4, that will make the coefficients for the y's opposites of each other. So that's what I'm going to do. And I've run out of room going across. So the second equation I am multiplying by a -4. First equation is staying the same. Of 16x, make sure you're multiplying both sides of the equations in each term by that constant. Okay, so now if we add straight down, we'll have 21x equals to, what is that, 7. And then if we divide by 21 on each side of the equation, we will get x is equal to 1/3. Okay. So now I'm going to substitute 1/3. I don't know, I think I might substitute it into the second equation. It won't matter if you wanted to substitute into the first, but I know I'm solving for y, so since y is already almost by itself, oops. Okay, so that will be 3y equals to 4/3 plus 1, and I can rewrite 1 as 3/3. So that would be 3y equals to 7/3. And if I divide by 3 on each side, which is the same as multiplying by 1/3 on each side of the equation, the reciprocal, I'll get y is equal to 7/9. Okay, and I definitely want to check this in the original equations. I know they're fractions, but we want to check to make sure we didn't make some sort of an error somewhere. Okay, so for the check of 1/3, 7/9, I'm testing in the original equations. So I'll have 5 times 1/3 plus 12 times 7/9 equals to 11. Move this over a little bit. So that would be 5/3 plus, so you can think of 12 times 7 divided by 9, or I know that 3 goes into 9 3 times, 3 goes into 12 4 times, so the 3 will divide out. 4 times 7 is 28 thirds. 28 plus 5 is 33. And 33 divided by 3 is 11. So the first equation checks, that's good. Checking the second equation. Okay, so dividing out a 3, I'll have 7/3 on the left side. And then 4/3 plus 1. Remember, 1 can be written as 3/3. So we get 7/3 equals to 7/3. So 1/3, 7/9 is the solution to this system. Okay, so to try this, you guys can try, well, actually, I guess I'll go over it. Okay, so we have equation 1, equation 2. Notice that the coefficient for the y is 1, and the coefficient for the y in the second equation is -2. So if I just multiply the first equation by 2, then the y's will have negative coefficient. Or, sorry, not negative, opposite coefficients. Make sure you're multiplying both sides of the equation. Okay, when we add together, we'll get x equals to -2. And I'm going to substitute back into the first equation. So if we add 4 to each side of the equation, we'll get y is equal to 1. negative 4 plus 1 equals negative 3. That is true. So we get 6 minus 2 equals 4, which is also true. Okay, so remember we have those special cases of when we have a dependent system. So all three of all of the examples we've looked at so far here were consistent systems because there was exactly one solution. So now we're going to look at what happens when you're using elimination method and you have a dependent system, so infinitely many solutions, or an inconsistent system, so no solution. Okay, so for this system, we have equation 1, equation 2. I'm going to multiply the first equation by negative 2 to make my goal right now. I'm thinking about making the y's opposites of each other, the y coefficients. So I would have negative 6x plus 2y equals to negative 14. But you probably already see it now. When we add straight down, well, we end up with 0 equals to 0. That's true. Okay, which means that there's going to be infinitely many solutions. This is going to be a dependent system. Write this. And to represent the solution set to a dependent system, there's infinitely many solutions, all the points that lie on the line. I'm going to have x comma, and then I have to pick one of these equations to solve for y. Remember, these equations are actually the same. They represent the same line. So I'm going to take equation 1 to solve for y. So negative y equals negative 3x plus 7. If I divide by negative 1, I get y equals to 3x minus 7. Okay, so this ordered pair, x comma 3x minus 7, remember you could think of as like a formula to find any point that lies on the line. And remember, both of these equations represent the same line. You could think of them as two lines that end up overlapping. So every single point that satisfies the equations will be part of the solution set. Okay, equation 1, equation 2. I'm going to multiply the first equation by 2 to get the x's to have negative coefficients. That's just what I see first. If we add straight down, we'll get 0 on the left-hand side, but we will get 30 on the right-hand side. Well, that's not true. So that means there's going to be no solution to the system, which you can use the empty set notation. And therefore, this is an inconsistent system. Okay, I'm going to leave the try this for you guys. So, clearing fractions, you guys know how to do this already. So, given a linear system where the equations have fractional coefficients, it's usually best to clear the fractions before beginning elimination method. So remember, we can drop a bomb to clear the fractions. So just using multiplication property of equality. So the bomb that you drop is the least common denominator. Okay, so the smallest common multiple of the denominators. Okay, so for this system, if this is equation 1 and equation 2, okay, I want to get rid of all the fractions in each of the equations. So the least common multiple of 10 2 and 5 will be 10. So I'm going to multiply the first equation by 10. The least common multiple of 7, 3, and 21 will be 21. Okay. So whenever I multiply each equation, so the first equation I'm multiplying by 10 on each side, that'll give me negative x, and you might need to do side work for this. But I'm multiplying each term by 10. So that gives me negative x plus 5y equals to 8. And then the second equation, I'm multiplying each term by 21. So I'll have 3x plus 7y equals negative 2. Okay, well this looks a lot more manageable. I still don't have coefficients that are opposites of each other, but we're almost there. So I'm going to now multiply the first equation by 3 in order to make the x's have coefficients that are opposites. Okay, so if I add straight down, that'll give me 22y equals to 22. You can divide by 22 on each side to get y is equal to 1. And now you can go to one of the original equations that have the fractional coefficients to solve for x, or I'm going to go, I think I'm going to use equation 1 in the second step here. So I'll have negative x, this is the second version, so I'm using this equation. So this is the second version of equation 1. So negative x plus 5 times 1 equals to 8. So if I subtract by 5 on each side, we'll get negative x equals to 3. Divide by negative 1, we get x equals to negative 3. Okay. And then clearing decimals, you guys know how to do this process as well. Multiply each equation by the lowest power of 10 necessary to result in integer coefficients. So if I have equation 1 and equation 2, I can multiply the first equation by 10, and then I'll have integer coefficients. And then the second equation, it looks like I have to multiply by 100 to get rid of the decimals. So I have 30x minus 6y equals to negative 9. And negative 50x, because it's multiplying by 100, we'll move the decimal over to the right 2 places, plus 12y equals 16. And then I'm going to multiply the first equation by positive 2 to get the y's to have opposite coefficients. So 60x minus 12y equals negative 18. So 10x equals to negative 2. Yeah. So dividing by 10 on each side of the equation, we'll get x is equal to negative 1/5. And I'll use the, it doesn't really matter, I'll use the first equation in the second step, so I'm going to use this equation. Uh, 30 times negative 1/5 is the same thing as 30 divided by negative 5, so that'll be negative 6 minus 6y equals negative 9. I can add 6 to each side of the equation, and then divide by -6 to get y is equal to 1/2. And then you guys have the u try. Okay. All right, so this is our last method. So elimination method will be our last method that we're going to look at for solving linear systems.